Welcome back to ECE 320A. Homework number 7 is due sometime during the week of the 8th, and I will post that the next time that we meet. It won't necessarily be on the 8th. It will be after that Sunday. Convolution material, which you need to do on your own, is posted on D2L. So after today's class, I hope that you have a feel for convolution, and then that material will allow you to mechanically perform the convolution process. That's the idea. And there's about 4 different lecture notes and videos available. They're not all 75 minutes in length. They're like 25, 35, but I need you to look at those to give yourself some more information about how to perform these convolution integrals. And I think it's maybe different from the strategies that you've seen in the past. Office hours this particular Friday are being moved. I've had a couple of different commitments come up, and so I'm going to try to make those at 11 o'clock to noon this Friday. And hopefully it will only be this Friday. Now, you'll tell me you have a class at that time. Okay, I knew not to schedule it at 9 because of 3:10, correct? Or 10 o'clock, which is 381 or 369. Thank you for reminding me of what we made for the schedule. Today, I want to motivate convolution by looking at a first-order circuit, finding its transfer function, finding its impulse response. I will try to derive somewhat intuitively the convolution integral so that you get a feel for where these terms are coming from. Why are the arguments on one of the waveforms flipped and shifted? And one of the notes that you have on D2L is concerning flipping and sliding, not slipping and sliding, but flipping and sliding, and intervals and limits. And hopefully those will make sense when you look at those. We will then compare the frequency domain and the time domain, and that comparison is really so that you don't confuse multiplication and convolution. Just quickly, frequency domain multiplication is equivalent to time domain convolution. So if somebody says, what's convolution in the time domain look like in the frequency domain? You can just raise your hand and say it's multiplication. That's what we will talk about. And then we'll try to get through an example. All right, let's get the neurons firing. And here is a quiz. I will give you maybe 30 seconds or a minute. Think about how you would find the transfer function between the input, which is X, and the output, which is a voltage, Y, in this circuit. I'm going to watch the clock and not give you too much time to think about that. Now that you have that, here's the second task. I want you to think how you would use that transfer function if you were now asked to find the output Y due to either x1 of t or x sub 2 of t, where x sub 1 of t in the time domain, let's say here's x1 of t, and let's just say that it's that waveform, or x sub 2 of t, how would you now find the output y given those two waveforms? If that's what you apply to your system's input, x, either x sub 1 or x sub 2, what would you get for your output y? And what would you expect the output to look like? This is maybe what I want you to be thinking about now. How would the output, let's say y sub 1 of t, what would it look like relative to x sub 1? Would it look at all like x1, or would it look different, and how would you tell that? And would your output due to the input x sub 2, would it look similar to x sub 2, or would it look different? And how much different? Can you find an expression for x sub 1 of t in terms of, let's say, elementary waveforms? By elementary waveforms, I'm meaning an impulse, a step, a ramp, a sinusoid, a cosine, an exponential. Those are standard waveforms. Can you write x1 of t as some linear combination of those? If it didn't have that stop at t1, that would just be a step, right? So we could say, and depending on what that amplitude is, let's say that it's a, this could be a u of t if it just went on forever, but we know it's actually stopping at t1, so we could just change that amplitude, reverse its amount at time t sub 1, and this now is some pulse of duration t sub 1 and amplitude a. And you now know how to find the output due to a step or a constant using Laplace transform. So you could actually find y sub 1 of t due to this x1. You would just sum the output due to each of these inputs. A turns it on, or the first one turns it on, the second one turns it off, and now you would have your result. What about x sub 2 of t? That's sort of a pulse, isn't it? It's a smoothed pulse. If that's actually sinusoidal, is it a cosine or a sine, basically? Sine. So this is like a sine wave. So now I could say, oh, that's equal to sine omega t, but I know that it's only on so I could basically tell it to be on at a given interval of time, which is now this windowing function that says, oh, you're only going to be 1 between 0 and time t sub 1. This is now a window. What's omega? That was a very generic question, so you could answer it with a very generic answer. Omega, 2 pi f. That's fine, right? That's what omega is. Omega is 2 pi f. F is in hertz, omega is in radians per second. But now that triggers, hopefully, some additional information. How is the frequency f related to the period of that waveform? They're reciprocals. In this case, what is the period? It's 2 times capital T sub 1. So if we know that f, or let's say let's say the period is 2t sub 1, then f being equal to 1 over t is 1 over 2t1. Now we know what omega is. Omega is now equal to 2 pi over t, or 2 pi f, or the omega is actually pi over t sub 1. Now, let's go back and see if we can find a transfer function given a system. And let's just stick with the system that I gave you to begin with, except now let's model this in the frequency domain. Our input now is the Laplace transform of our input waveform. The output is the Laplace transform of the output that we expect. And what are the impedances of those two circuit elements? What's the impedance of the resistor? That's whatever it was given as R. What's the impedance of the capacitor? That's 1 over SC. But now what I want you to do when you see something like this, I want you to start to think, oh, this is just some impedance and another impedance. Let's say this is now Z sub 1 of S, and this is Z sub 2 of S. And those could be much more general than what I've indicated here, but now for those particular values, Z1 is just R, and Z sub 2 is 1 over SC, but now I can treat those Z's like I treated resistors in 220, except now my resistors are a function of S. Not a problem. We'll just end up with ratios of polynomials in S, and we know how to inverse Laplace transform those. If those were resistors, how would we solve for Y given X? Voltage divider. Now we can just do a voltage divider and say, oh, this transfer function stuff is easy. Y of S is now simply Z sub 2 of S, that impedance, over the sum of the two impedances, times the input. And what's in square brackets is the transfer function that I was asking for before. And if we plug in specific values or expressions for Z1 and Z2, we can now say that capital Y of S is equal to 1 over SC all over R plus 1 over SC times X. That's a little bit ugly because it's a ratio of ratios, but the numerator and denominator, we can actually find a common denominator between the two, which is just SC. If we put the numerator over SC, which it already is, and the denominator over SC, we just have to change R to SRC. And then those SC's cancel, leaving us with 1 over SRC plus 1 as our transfer function. Did everyone get that for your transfer function? Question. So the transfer function is only defined, the question was, is it only defined in the frequency domain? And yes, that's how we are defining a transfer function. We now want it in the frequency domain. And in the time, we're going to find the equivalent form of this in the time domain, and that's going to actually be the impulse response. The little h of t corresponding to this capital H of s. This particular transfer function, what's the order of this transfer function? And you could have told me that from the circuit. Yes? How many energy storage devices were in that circuit? 1. So you knew you were expecting a first order transfer function. This particular transfer function is actually in a specific form called time constant form, meaning the constant has been normalized to 1, the constant term. And our time constant, tau, is what's scaling the s. Tau is RC, where tau is our time constant. The time constant form of that transfer function can be contrasted with a pole zero structure or pole zero form of the transfer function. If I now factor out that 1 over SC from the denominator, if I factor out the RC, now I have this transfer function written differently. It's equivalent. It's exactly the same transfer function. It's just now this is in what I call pole zero form. The poles and the zeros are explicitly found by looking at these factors in the numerator and the denominator. Where are your finite zeros? Or how many finite zeros do you have? You do not have any, do you? You do not have a finite zero. There's no finite value of s that causes that transfer function to equal 0. Is there an infinite zero? Yes, if you let s go to infinity, h of s would go to 0. So you do have 1 0 at infinity. If somebody starts talking about infinite zeros, you have a clue as to what they're talking about. Where's your pole? At minus 1 over RC. Let's now take this. Now that it's in pole zero form, can you inverse Laplace transform that? That implied notation is saying inverse Laplace transform of h of s gives me little h of t. You now have s plus a in the denominator. What's that inverse Laplace transform? E to the minus at. So this should be e to the minus a is 1 over rc times t. Is there any scaling? This was not 1 over s plus a. This was a scaled version of 1 over s plus a, and the scaling was 1 over rc. And this is true for t greater than or equal to 0. And like I said, this expression is given a specific name, and that is the impulse response of that circuit. And you just have the one mode, the one exponential term. It's a first order. And this means what? What's the impulse response tell you about this circuit? It's its response to kicking it. That's, okay, so you're trying to keep me from kicking something. I'm wanting to kick something, and I don't have a ball. And that's a problem. So now I just have a desk or something. Somebody has a ball? Oh. Yeah, I don't want to kick any one. I'll kick an inanimate object. How's that? Or myself. So, now you have an impulse response. You hit the system with an impulse, and this is what you see. Where does it start at time 0? 1 over RC. How long do you see this response? 5 tau. And what's tau? RC. So tau is RC. 5 of those is how long you would see this exponential. And then it's basically 1% of 1 over RC, which is, we're assuming, is negligible. If we wrote that in terms of the time constant, you said tau was RC, or that's what I had told you. This is, another way of writing it, is 1 over RC e to the minus t over tau. And you've maybe seen expressions written that way, e to the minus t over tau. That allows you to immediately find what your time constant is. If you had a bunch of these e to the minus something t's, you could say, let me set those equal to e to the minus t over tau and solve for tau to find my time constant for that particular mode, or that exponential. And you already told me, so that was h of t, the pole of that was when the denominator was equal to 0, and we had 2 denominators. If we go back to the time constant form, we set that denominator equal to 0, and the pole is the value of s that satisfies that equation, or that's now at minus 1 over SC. Now, not only do you see that circuit, but you should start to see poles and zeros populating in the S-plane, or X's and O's on this S-domain diagram. Where are my zeros? Do I need to draw any open circles? No, I didn't have any finite zeros. What about poles, X's? I just had the 1, and that was at minus 1 over RC. And now you're saying, so what? Here's the real part of the complex variable S, and here's the imaginary part. Do you see a circus? Do you know what I'm talking about? Circus, not circuit. So you started with a circuit, you went to the S domain, and now you see a circus. What? What are we looking at? A big top tent, right? You now have a rubber sheet laid on top of this S-plane, and what's underneath that rubber sheet? A circus. Very good. And that circus is performing underneath a top, isn't it? A big top. And that top is suspended or supported by that one pole. Now if I walk along the imaginary axis and look up, I'm seeing the frequency response, which is how your stereo would respond if you had a graphic equalizer set to that big top tent's shape that you're walking underneath. What does that look like? How can we sketch that based on this diagram? Well, we can actually graphically sketch it. If we bring out our drafting tools, we have our dividers, we have our t-square, How many have a t-square at home? Really? Yay! Good. Now dividers. Who has dividers? I have a divider in my office. Does that count? No. Mechanical dividers that you're drawing with. They have little sharp pins. You don't want to see them thrown across the room. Ow! They're like darts. 2 darts on the end of sticks. But they measure distances. Those are your dividers. Okay, no one has those. But what we want to do is try to figure out how does this circuit behave as a function of frequency, and can we do that by looking at this pole zero diagram? If I ask you what is this guy going to do at DC, what would you tell me? How is this circuit going to pass DC signals? By looking at that transfer function, what are you looking at? If I said a DC signal, what's the S? What is S equal to for DC? S is a frequency, and DC is at 0 hertz, isn't it? S is 0. If you plug in 0 to S, what do you have for that magnitude of the transfer function? 1 over RC over 1 over RC, or 1. So this says that if you put in a constant, you're going to see that same magnitude constant at the output in that circuit. What if you put in a higher frequency? Now what are we doing? Now we're actually walking. We just found what would happen if we put in a signal right there. What did we do? Well, we measured the distance from that pole to there, and that's actually giving us this length. And that length, back to the origin, was 1 over RC. And we divided that into that length. Now, what if we increase the frequency up a little bit? Now what do we do? Well, now the distance from that pole to that frequency, this is now J, let's say omega 1. Let's say omega 1 is about 1/3 of 1 over RC. Now do you see that that length is getting a little longer than it was at 1 over RC? It's now a hypotenuse that has a little bit of vertical distance on that triangle. And we're dividing that into the same 1 over RC. So what's happening to our magnitude as a function of frequency? It's going down, isn't it? If we keep doing that, suppose I keep marching up the imaginary axis, that denominator distance just keeps growing. And then we have a special point right there, which is actually the same distance vertical as I was horizontal. And hopefully that's close. I don't have my dividers to make it exact. But do you see what I'm saying? Now I've walked up that imaginary axis the same distance that that pole is into the left half plane, a distance of 1 over RC. We are going to develop techniques or strategies to do these sketches rather quickly without looking at all of these points. We are going to develop strategies and say, you know what? Up until the time we get to that point, I'm just going to assume that my distance is 1 over RC. And then after that point, I'm going to start rolling off. Then I'm going to start taking this length into account, and I'm going to roll off as one pole factor would roll off. Meaning, if we now went to our graphic equalizer and started sketching H of j omega in dB, where dB is 20 log of the magnitude, we now are looking at sketching the magnitude of this transfer function as a function of frequency, but the magnitude is expressed in dB. And what I just tried to say was right here, at a frequency of 1 over RC, when we marched up the imaginary axis to that point, which is the same distance vertical as we were in the horizontal location, we are going to assume that the denominator, we're still going to approximate that as having this length of 1 over RC. So that this is now 0 dB. And after that, it will start to roll off, and because it's a log scale, we can draw these lines as straight lines. That's supposed to be a straight line, and this is now going down at minus 20 dB per decade. And that's now the graphic equalizer's frequency response. This is how you would shape those knobs on your stereo. You would have the low frequency out to some mid-range value of 1 over RC, and then you would start ratcheting that magnitude down. In actuality, what do you know is happening? Well, you know that this magnitude is always decreasing, and this is, let's say, the blue line is the straight line, approximation, and the dashed black line, and the blue line is the one that we will focus on. This is the actual magnitude response. And this particular point right at the, and this is called the break frequency, this guy right here, I'm giving you a lot of different terms. And that's not related to break dancing, but they're all dealing with sometimes music frequencies. And so this is the break frequency. That's where that magnitude breaks or starts to transition. Have you heard of what happens at the break frequency in terms of your magnitude, how much it's going to be down in dB? 3 dB down. So this is actually the minus 3 dB point. That's the actual magnitude, and where that's coming from is if you now look at h of j omega, which is really the h of s evaluated at s equal to j omega, we've now replaced s with j omega. This is now 1 over RC over 1 over, you do it in the time constant form, this is now RC times j omega plus 1. So that now, if we actually didn't worry about this guy, if we now looked at when omega is equal to 1 over RC, what's the denominator going to do? That's this j plus 1. So that if we were looking at the magnitude of that denominator, we could say that's the square root of 1 squared plus 1 squared, or the square root of 2. And if we put that into this log base 10, square root of 2, and if this was now 20, and this was actually in the denominator, so it would be raised to the minus 1. It's 1 over that. Now we get to play with what logs allow us to do. We have 20, but we can take that exponent to the front. We have 20 base 10, and the square root of 2, that can be written as 2 to the 1/2. That 1/2 can now jump out front. We have 20 minus 1, 1/2 log base 10 of 2, or this is now minus 10 log of 2, and you probably have the log of 2 memorized. Anybody have a calculator? What's the log of 2? You knew what the answer needed to be, so you just divided it by 10, and it's 0.3, isn't it? It's 0.301, so we approximate that to 0.3, which gives us, so this is now approximately 0.3, and there's our minus 3 dB that we were looking for. And this shape that we've sketched here for our magnitude, that's the behavior of a first-order low-pass filter. That's the magnitude response of a first-order low-pass filter. Now, in general, if we start with a transfer function, capital H of S, what happens to the output when we hit the system or we kick the system? We hit it with an impulse. Suppose the input is an input, in an impulse. X of t is now an impulse. We said x1 at one point was this pulse, and x sub 2 was this sinusoidal pulse. Now we're saying what happens when the input is in fact just an impulse. Do you remember how to Laplace transform an impulse? If you plug that impulse into the function of your Laplace transform definition, what happens when you use that impulse inside an integral? It's now going to give you a result of 1. That's now going to sift out that, that's what that was, sifting. If you needed to do some baking, you would sift. Most flour is now pre-sifted. You don't have to worry about it. You just go and buy it off the shelf. You don't have to have a sifter. Extra household appliance you don't have to purchase anymore. Now you need to go out on somewhere and buy it, right? Just to get one, bring it in and set it on the desk. With your divider, you now have a sifter to match your t-square. Now, if we know capital X of S is 1, and we want to know the output, we know in the frequency domain the output is just the product of the system's transfer function, capital H of S, and the Laplace transform of the input. But if this guy is just 1, now the output in the frequency domain is just the transfer function's transfer function. And that allows us then to conclude that in the time domain, the output y of t, which is simply the inverse Laplace transform of the output, with the input being an impulse, that's equivalent to the inverse Laplace transform of that transfer function, which we call little h of t, and we've already called this today the impulse response. And the impulse response is just the response of our system, whatever that is, capital H of S, to an impulse function or waveform applied at the input. That's the impulse response. And we know now how to relate the output, capital Y of S, the system's transfer function, capital H of S, and the input of our system, capital X of S. We know how to do that in the frequency domain. What we want to know at the end of today is how are those related in the time domain. How are X of t, H of t, the impulse response, X is the input, H is the impulse response, and Y of t is the output. How are those three waveforms or time domain functions related in the time domain? That's what we want to talk about now. And that's where I am headed when I say this is now our chance to develop the convolution integral. Do you know what that is, just from memorization? Do you remember what the convolution integral is as an expression? If you say no, that's fine. That's a valid answer. I was just curious. No? Okay. Let me write it down so we know where we're headed. This is now the integral, and this is our variable of integration. Let's just call it lambda, from minus infinity to infinity. H, you know what that is. Y is our output. H is the impulse response of our system. We take the argument of our impulse response as t minus lambda. We multiply that by our input as a function of lambda, where lambda is our variable of integration. Or, if you wanted to, you could write that by reversing the arguments on the impulse response and the input. We could say we have h of lambda, x of t minus lambda, d lambda. We can solve it either way and we'll get the same answer. The h's that's our impulse response, and the x's are the input in the time domain. We want to be able to feel comfortable with that expression and actually solve these integrals or compute these integrals in the time domain. That's homework assignment number 7. We want to be able to find h's, and we need to be able to find y's for different shapes of x's in the time domain, because x may not be always in our table of Laplace transforms. It may be something more general, something a little bit more abstract. The picture that you need to be thinking of now, you're moving, let's say, above just always thinking about circuits. Now you have some linear system we now can think of that as having some impulse response. That describes how this system behaves. If we know what this system does when we kick it, then we can find how it will respond to any x we apply to that. That's what this convolution integral allows us to do. So if we can find the impulse response of this linear system, we can then solve for any output that somebody wants if they give us the input that they applied to the system. Now, let's go back to what we already know. Suppose that let's look at some example inputs and outputs. Now we're trying to find where these are coming from, this convolution integral. Where did that expression come from? And let's do it by going back to what we're comfortable with. Suppose that I give you an input there's time, and let's now say x sub 1 of t is now an impulse. Oh, let's give it an amplitude of a. It's not an amplitude, a weight. A weight on this impulse. The amplitude is infinite. The weight tells us how much area is underneath that if we integrated from 0 minus through 0 plus. We would get an area underneath that weighted impulse of a. If this is x sub 1 of t, what's the output? In terms of y, h, and x. y1 of t equals. So I'm now telling you that you can use x, h, and y in your output, and I've already used up y. But you have, let's say, knowledge of the impulse response of this system. And now what are you applying at the input? What's the input? An impulse. And we know how the system responds to an impulse. That's h. So now all we have to do is weight that by a. The output, in fact, for this system is now a h of t. It's just the impulse response weighted by however much we've weighted the input. And if let's say that we had some maybe first order behavior, first order filter, this might look like that. That might be our y sub 1 of t. That's a legitimate decaying exponential for a first order impulse response. So we hit this system with an impulse and we get this exponential decay. Now, suppose, is everybody comfortable with that? Where all of these terms are coming from. It's just defining and using these terminologies. We had our system described by its impulse response. I give you an input, which in this case happens to be an impulse, and I say, what's the output? Well, I know the impulse response, and he gave me an input as an impulse. It must be the impulse response that's weighted by however much weight was on that input, and that was A. Clear? All right, let's step it up a notch. So now suppose that I say, here's another input. Let me call it x sub 2 of t. It's going to be a big step. Suppose that I now apply an impulse at time tau sub 1. And that impulse is weighted by A. What is y sub 2? it's going to be weighted by A. It's going to be the impulse response, right? Because I'm hitting the system with an impulse. It's just I've delayed that impulse. So my system is not going to respond before I hit it, and it's going to respond right when I hit it at tau 1. So this is now A, H of t minus tau sub 1. And if we drew the picture, that's what y sub 2 would look like. The same exact picture for y sub 1, it's just now been translated or delayed by an amount, tau sub 1. All right, that wasn't too big, right, of a step. That was, everybody clear on that? We're learning how to crawl before we start sprinting. How's that? Suppose now that x sub 3 of t, the input, is x sub 1 of t, the impulse at 0 with a weight of A, and another impulse with weight A at time tau sub 1. What's y sub 3? It's those two right-hand outputs, isn't it? And I'm going to write it compactly. I'm just going to say, well, that's just y1 of t plus y sub 2 of t. But you can see that those are those same delayed impulses with the appropriate weights of A on each of those impulse responses. Now, what we need to do is take that more general. Suppose now, if the input, let's say x of t, has the following shape. Let me now take x of t to be that. And maybe I'll call it x sub 4, just so we have it not as just x. Let's say this is our input, x sub 4 of t. What is y sub 4 of t? Why did you go from crawling to sprinting in one step? Well, just back off. Let's think this through. Let's try to figure this out a little bit. What if I said, you know what, if I somehow had an impulse right there, I'd know how to solve it, right? And if I had an impulse right here, I'd know how to add that in. And if I had an impulse right there, I would know how to get the answer. If I had an impulse, and I've tried to center those taus underneath those particular sort of different shapes on X. Well, what did that weighted impulse do? That was just giving me the area under that curve, under that input. What if I now take and say, why don't I look at this? Let me just assume, for illustration, that the width is 1. And now what's the area under this curve? If the width is 1, the area is length times width, and now the width is 1. It's just the height of that. Let me call that now x sub 4 at time tau sub 1. Is that okay? That's the area underneath, or in that red crosshatched space. What about here? And now, again, my picture's maybe not very accurate. Again, I left my dividers at home. That's supposed to be 1 also. But this area that's just x sub 4 at time tau sub 2. Is that seeming okay? Are you uncomfortable with where these numbers are coming from? And now let's do that over here. Again, the width is 1. This area is x sub 4 of tau sub 3. All right, now I've said, let's take those areas and move forward or go back to how we know how to work this problem. We know how to work this problem if our inputs were impulses. We know roughly where to put those impulses. Let's put them right at tau 1, tau 2, and tau 3, and then you'll be able to give me an answer. An approximate answer, but it's an answer. That's what you need to feel comfortable doing. Let's maybe not get the exact answer, but let's give you an approximate answer. Well, here's some area that I'm applying to this signal, this system's impulse response at tau 1. Here's a little bit more at tau 2, and here's a little bit at tau 3. I know how to do that. If I now say, let me approximate x sub 4, and just say as a function of time now I'm going to approximate my input, that square sort of shape. Let me now create that and say, oh, here is at tau 1, this is now x sub 4 at tau 1. At tau 2, that's now x sub 4 at time tau sub 2. And at tau sub 3, that has a weight of x sub 4 of tau sub 3. If that's my input, what's my output? And you told me before that you were comfortable crawling with these impulse input signals to generate an output. Well, now we've approximated this waveform as just a sequence, a string of impulses. What is y sub 4? Now I have an impulse with weight x sub 4 of tau sub 1. What's the output due to that? I'm hitting the system with an impulse, and you already know the impulse response. You know it has to be a weighted impulse. And how is it weighted? By the weight on the impulse. This should be x sub 4 of tau sub 1. That's the weight. And now what's the h? When does it start? When that impulse occurs at tau 1. Is it clear where that's coming from? That's just x sub 2 that we had before, just a delayed impulse. And we're now finding the piece of the total output due to one of those 3 impulse waveforms at the input. What else do we have? Well, we need to add the other 2 in. The second one now is x sub 4 of tau sub 2. That's the weight. And what's the h? T minus tau sub 2. And finally, the weight on that last impulse is x sub 4 of tau sub 3, that's going to scale the impulse function delayed by an amount when that time starts. Question?
So, I guess like graphically, the tau equals start of the impulse.
So now, so the question was, I think, arguing with my approximation a little bit. So so the question is, how fine do I need to worry about where tau 1 is located? Right now, don't put too much emphasis. You know your insight is correct. You know you're going to start seeing some output as soon as the input is applied. That's what you're getting messed up on. And that's fine. That's where you should be getting a little disconnect. What I'm saying is, let's just approximate that whole piece as starting maybe a little bit off from when it really does, but let's just approximate that whole thing as happening at one point in time, and that's tau 1. So yes, it's going to be an error, but do you see that if I start making these approximations or this division of my input at finer and finer times, excuse me, at finer and finer times, we're going to get that tau 1 to be right on top of where it really needs to be. So this is just a crude approximation that we are trying to get comfortable with this convolution integral expression. So yes, there is some error in where we've maybe located tau 1 relative to when the signal starts, but we're going to tolerate that in this approximation. Did that help answer your question? Question.
So what we're trying to get at is that by adding these functions to y, if we do this for cost, it's the same thing as the multiplication of them.
So we are going to now, what we're trying to do is derive the convolution integral. And that's going to, we can show that that's equivalent to multiplication in the frequency domain. We haven't really worried about that right now. We've been working exclusively in the time domain. And I want you to feel comfortable with what we've done up to this point. And there is a little uncomfort there as far as tau 1 is right in the center of that and it starts a little before. That's okay. We're going to just brush over that. But what do we have now? I can now say that y sub 4 of t is now this sum from, let's say, L equal 1 to n. If I started making this a little bit finer, chopping it up and making more taus, I could say, oh, that's x of tau sub L, h of t minus tau sub L. Do you buy that? If I started making more and more slices of my time axis, this is now what I have. And I think you know where I'm headed. In the limit, as we enhance the accuracy of our approximation of x sub 4 of t, right now this is a finite sum with capital N pieces. The finite sum turns into what? An integral, right? This sum now becomes an integral when we keep dicing it up finer and finer. So that now we can, if we look at this expression for y of t is now going to be, instead of a finite sum, it's an integral. And who knows when we're starting and who knows when we're finishing, so let's just say it's from minus infinity to infinity. We have x of tau, h. Do you see the corresponding t and h with the t and y? That argument is t. This is now t, and we were basically summing over minus tau and tau in h and x respectively. This is now tau d tau. And that is what we were trying to derive. This is now our convolution integral. And this is how, in the time domain, our input, x of t, our impulse response, which is a time domain behavior of our system, how that is combined or used to create our output. It's no longer a multiplication, is it? This is some way of multiplying these time domain waveforms, and in fact, we are going to say that h, in this case, is flipped. The variable of integration is tau. We're actually negating that. That's what I mean by flipping it. And t, we want to find y for all time, from minus infinity up to infinity. This is now tau equal to minus, that's our variable of integration, but t is also allowed to go from minus infinity to infinity. If I give you a value of time t, let's say 6, then you would have h of 6 minus tau. Then we might want to find what is y of 7. We would plug t in of 7, and we would have h of 7 minus tau. So we're flipping h, and we're sliding it 6, 7, 8 through time. That's where this flip and slide comes from. And we also need to figure out where the limits of our integration need to go, because our waveform might change shapes, and that's this limits and intervals piece of the process of doing convolution. Are there questions on this? Let me try to get into an example, and we'll come back next time maybe to the relationship, or just stating that multiplication in the frequency domain is equivalent to convolution, this guy, in the time domain. Let's see how we can do this. Let's see if we can get started on a convolution example. Suppose that somebody says, here is an input, x of t, that I want to apply to a system, and I'm assuming that this input begins before time 0. It starts at minus 3 and ends at 3, and it has an amplitude of 5. And let's say that the system that we're applying this to has an impulse response given by h of t, and that impulse response, let's say, starts at 2 and decays exponentially. Let's say that this is now 2e to the minus 2t. And now we want to know, what is y? What's the output when we apply this input x to that system that has an impulse response that's 2e to the minus 2t? Is that impulse response, what kind of a system is it associated with? A first order. And you could consider it a low-pass behavior. It's now this exponential shape that has actually a pole at s equal minus 2. You know that just by looking at the exponential. You now want to perform this convolution, and in this case, you can flip and slide either x or h, and it doesn't matter. In this case, it's going to be easier to flip and slide x than flipping and sliding h. I just like to flip the ones that have the less involved shape or functional description, and that's x. So now what we're trying to compute is y of t, which is this integral from, let's say, minus infinity to infinity of h of lambda x of t minus lambda d lambda. That's what we want to compute. We want this. What's h of lambda if h of t looks like this? What's h of lambda? You know h of t, you then know h of lambda. Just replace t with lambda. That's h of lambda. That's about as easy as it gets. So we now know h of lambda. H of lambda in this integral is going to look just like h of t, except now it's a function of lambda. This is now 2, and this will be 2e to the minus 2 lambda. That's h of lambda. What we want to do now is find x of t minus lambda. We want it to be a function of lambda, and t is a variable. And there is x of t. First, let's now look at, if that's x of t, what is x of lambda? And that's exactly the same answer that you gave me for h. If I give you x of t, and now I say what's x of lambda, what's x of lambda? It's just what x of t was, except now I replace t with lambda. Has exactly the same shape. It's now minus 1 to 3, and it's 5. What is now x of minus lambda? Now you just have to get on the vertical axis and rotate, right? Just take x of lambda and spin it across the imaginary or the vertical axis. Now I'm dizzy. Good thing I only rotated 180 degrees. I just need to go minus, right? So now this point that was right here moves over here. Is that clear? We just rotated x around the vertical axis. That's now x with a negative argument. Now what we want to do is we need to consider t as a variable what's x of t minus lambda going to look like? Now I'm going to be adjusting t from minus infinity all the way up to plus infinity, but I now want to just leave it as a variable t. If I now said t was equal to 0, do you see that I would get x of minus lambda? So whatever I draw down here for x of t minus lambda, it better return x of minus lambda when I replace t with 0. What if I put something like this? I know that my shape looks like that. It's going to have a magnitude of 5. What's this endpoint going to be? If I let t equal 0, will that shift up and be equal to x of minus lambda? What about this endpoint? Is it clear where those endpoints are coming from? So now as t goes from minus infinity, I'm way over here, and I'm going to adjust t from the left and just keep varying t to find y of t for all those values. And x is going to slide across that lambda axis as I vary t from minus infinity to infinity. What I now need to do next time is use this, x of t minus lambda, scale it with h of lambda, and evaluate that integral. And we'll find that we have different patterns associated with the way those waveforms overlap or lay on top of each other, and we'll try to evaluate those different regions. We'll see you on Thursday.